Between the galaxies you have seen in every photograph, between every cluster and supercluster astronomers have ever mapped, there is something far larger than all of them combined. It is not a wall of galaxies. It is not a supercluster stretching across billions of light years. It is almost nothing, a region of space so staggeringly vast and so profoundly empty that it dwarfs every structure the universe has ever built. Scientists call it a cosmic void. The largest one ever discovered spans nearly 2 billion light-years across, a region of space where 1 in every 5 galaxies that should exist is simply missing. What makes it terrifying is not what lurks inside this region. It is what the void reveals about the universe itself. Most of it is missing. If you enjoy journeys that permanently change how you see reality, do me a small favor and hit that like button and subscribe. It genuinely helps this channel keep making content like this, and I truly appreciate every single one of you. Now, let's begin. For most of human history, we assumed the universe was more or less evenly filled with stars and galaxies. It seemed reasonable. Point a telescope in any direction, and you will find something shining back at you. The night sky looked crowded, peppered with matter sprinkled in every direction as far as instruments could see. Astronomers spent centuries cataloguing this apparent abundance, counting nebulae, mapping star fields, classifying galaxies by their shape. They were building a picture of a cosmos that seemed, at its largest scales, satisfyingly uniform. Galaxies were everywhere, and everywhere looked roughly the same if you zoomed out far enough. This assumption was so deeply embedded in modern cosmology that it earned a formal name, the cosmological principle. The universe, viewed at sufficiently large scales, should be homogeneous, the same in every location, and isotropic, the same in every direction. It was elegant, mathematically convenient, and appeared to match every observation available. Then, in the late 1970s, that picture was torn apart. The collapse began with a deceptively simple ambition. Astronomers wanted to build a 3-dimensional map of the universe. Every sky survey they had made up to that point was essentially flat. They could tell you where a galaxy appeared on the sky, its coordinates projected onto the dome above the Earth, but they could not tell you how far away it actually was. 2 galaxies sitting side by side in a photograph might be separated by billions of light years in real space, one relatively nearby and the other staggeringly distant. Without the 3rd dimension, without depth, astronomers were trying to understand a 3-dimensional structure using a 2-dimensional picture. It was like trying to map a mountain range using only its shadow on the valley floor. You could see that something large existed, but you could not tell whether 2 peaks were next to each other or miles apart in the direction you could not measure. The tool that finally cracked this problem was redshift. As the universe expands, it stretches the fabric of space, and light traveling through that expanding fabric gets stretched along with it. Wavelengths lengthen, shifting toward the red end of the spectrum. The farther a galaxy sits from Earth, the more the intervening space has expanded since that light was emitted, and the more its light has been reddened. By measuring the precise degree of redshift in a galaxy's spectrum, astronomers could calculate its distance. This technique was not new. Edwin Hubble had used it decades earlier to establish that the universe was expanding in the first place, but applying it systematically to thousands and eventually tens of thousands of galaxies in a coordinated survey was a project of an entirely different magnitude. It required new spectrographs capable of splitting light from faint, distant galaxies into their component wavelengths. It demanded enormous amounts of telescope, time spanning years of observation, and it required painstaking data reduction, turning raw measurements into precise 3-dimensional positions galaxy by galaxy. In 1978, 2 teams working independently began publishing the first results, and both found something that defied expectation. Stephen Gregory and Laird Thompson mapped a wedge of the sky in the direction of the Coma galaxy cluster, plotting the 3-dimensional positions of galaxies across hundreds of millions of light years. The distribution was not smooth. It was not even close to smooth. Galaxies clumped together along elongated chains and concentrated at certain distances while leaving enormous gaps between them. Regions tens of millions of light-years across appeared to contain almost nothing. Where the models predicted a relatively even scattering of galaxies, like grains of rice spread across a table, the data showed something shockingly different. Galaxies arranged themselves along narrow structures separated by yawning voids. The uniformity that cosmologists relied upon, the assumption that had simplified their equations and anchored their models, simply was not there. The universe had structure at scales nobody had prepared for. At almost the same time, astronomers Murat Jovir and Can Einasto at the Tartu Observatory in Estonia arrived at strikingly similar conclusions from a different portion of the sky. In 1978, they announced that the universe had a cellular structure, with galaxies arranged along the walls of enormous cells that enclosed vast, largely empty interiors. The claim was radical. The prevailing model assumed that matter distributed itself randomly and smoothly at large scales, a foundational assumption baked into the governing equations of cosmological physics. The idea that the universe was organized into walls and holes sounded almost architectural, as if the cosmos had been built according to some hidden blueprint. And the most provocative part of their finding was not the walls themselves, it was the enormous emptiness those walls surrounded. The cells they described were not small gaps between neighbouring clusters. They were vast hollow regions spanning hundreds of millions of light-years, and there seemed to be a lot of them. The confirmation came fast. Throughout the early 1980s, larger redshift surveys began mapping deeper into space, and every one of them found the same disturbing pattern. Galaxies were not uniformly scattered through the cosmos. They formed intricate networks of filaments and walls that enclosed enormous bubble-like empty regions. The deeper astronomers probed, the more organized the universe appeared, and the more prominent the emptiness became. Margaret Geller and John Huchra at the Harvard-Smithsonian Center for Astrophysics produced one of the most famous visualizations in astronomical history with their CFA redshift survey, a slice of the cosmos that revealed galaxies strung along thin arcs and walls surrounding conspicuous empty bubbles. The universe looked less like a smooth ocean and more like a sponge, a vast three-dimensional lattice of matter surrounding pockets of almost nothing. The more astronomers mapped, the more holes they found, and the holes kept getting bigger. The most dramatic early demonstration came in 1981. Robert Kirshner, Augustus Oehmler, Paul Schechter, and Stephen Schechtman had been conducting a redshift survey of galaxies in the constellation Boötes when they stumbled onto something that should not have existed. In a volume of space approximately 330 million light-years in diameter, they found fewer than 60 galaxies. 60. To appreciate how extreme that deficit is, you need to understand what that same volume should contain. A typical region of that size in the observable universe, based on the average density of galaxies measured across billions of light-years of surveyed space, should hold several thousand galaxies. The Boötes void was not just a little sparse, it was a desert, an enormous sphere of cosmic real estate from which galaxies were almost entirely absent. If our own local group of galaxies existed at the centre of the Boötes void, the nearest major galaxy cluster would lie so far away that it would barely register even in our most powerful telescopes. The night sky, stripped of almost all external galaxies, would look profoundly lonely. The discovery made headlines and created immediate tension within the cosmology community. A void that large was difficult to reconcile with the standard model of how structure forms. In the prevailing picture, the universe began in an almost perfectly uniform state after the Big Bang, with minuscule density fluctuations seeded by quantum processes during the first fraction of a second. These fluctuations were extraordinarily tiny, variations of roughly 1 part in 100,000 from the average density. Yet over billions of years, gravity amplified those fluctuations. Regions with slightly more matter than average attracted even more matter from their surroundings, growing progressively denser. Regions with slightly less matter lost what little they had to their denser neighbours, becoming emptier. This process, called gravitational instability, was well understood mathematically. It had been modelled extensively and produced results that matched many observations of cosmic structure, but producing a void as enormous as the one in Boötes required initial conditions that were statistically uncommon. The models predicted plenty of small voids, modest underdense pockets tens of millions of light-years across scattered throughout the cosmic web. A void stretching over 300 million light-years pushed the boundaries of what random fluctuations could comfortably produce within the standard framework. Some cosmologists argued that the Boötes void was simply a rare event, a statistical outlier sitting at the extreme tail end of the probability distribution, improbable but not impossible. Others suspected it signaled something deeper, a clue that structure formation was more vigorous and more extreme than the existing models predicted. And yet, regardless of the debate, the void was real. Confirmed and measured from multiple independent surveys, it could not be dismissed as a data artifact or a calibration error. The Boötes void forced cosmologists to take the structure of emptiness seriously, not as a curiosity in the background of galaxy maps, but as a fundamental feature of the universe that demanded explanation. But understanding what a cosmic void actually is requires clearing away a common misconception. A void is not a hole punched in space. It is not a region where matter was removed or destroyed or never existed. It is not the absence of everything. A cosmic void is a region where the density of matter, meaning galaxies, gas, and the invisible scaffolding of dark matter, falls far below the cosmic average. The universe has an average density, a number calculated from the total amount of matter spread uniformly across the total volume of observable space. Dense regions like galaxy clusters exceed this average by large factors, sometimes by hundreds of times. Voids fall below it, typically containing only 10 to 20% of the matter found in an average region of comparable size. That means voids are not truly empty. Galaxies still exist inside them, scattered thinly through the darkness like isolated farmhouses on an enormous plain. Stars still burn, gas still drifts in tenuous wisps too diffuse to collapse into anything new. Dark matter still permeates the volume, forming a ghostly web of invisible mass that connects to the denser structures outside. But the matter is so sparse, so spread thin across such colossal distances, that the gravitational forces which build structure elsewhere simply cannot operate effectively inside a void. This distinction between empty and underdense matters enormously for understanding what voids do to the universe around them. An empty region, a true vacuum with absolutely nothing inside, would be inert. Just space. Nothing happening, no forces acting on anything because there would be nothing to act on. An underdense region is something far more interesting and far more consequential. It is a place where the balance of cosmic forces tips in a fundamentally different direction. In the dense filaments and clusters where most galaxies reside, gravity is strong enough to pull matter together, resist the expansion of space, and build ever larger structures over cosmic time. Clusters grow by swallowing their neighbours. Galaxies merge in violent collisions that trigger bursts of star formation. Matter accumulates in the nodes of the cosmic web, like water collecting in the lowest points of a drainage basin. Inside a void, gravity loses that contest decisively. There is simply not enough mass to generate significant gravitational attraction across such enormous volumes. The dominant force becomes dark energy, the mysterious pressure that drives the accelerating expansion of the universe. In dense regions, gravity fights dark energy to a standstill or even wins, holding structures together against the outward push. Inside voids, dark energy wins outright, and when dark energy wins, space expands faster. The void grows. This creates a feedback loop that shapes the evolution of the entire cosmos. As a void expands, it becomes even more underdense because the same scarce amount of matter now occupies a larger volume. Less density means even less gravity. Less gravity means even less resistance to expansion. The void grows faster, becomes emptier, and accelerates its own growth in a self-reinforcing cycle. Meanwhile, the matter that once occupied the expanding void gets pushed outward, swept toward the boundaries where the void meets the surrounding filaments and walls. The dense regions get denser as this expelled material piles up along the edges. The empty regions get emptier as matter drains away. Over billions of years, this cycle carved the universe into the architecture we observe today, a web of matter enclosing bubbles of near emptiness that grow steadily larger and more extreme with cosmic time. After the Boötes void, discoveries accelerated. The technology improved dramatically with each passing decade. The 2-degree field galaxy redshift survey in the late 1990s mapped over 230,000 galaxies in the southern sky, producing the most detailed three-dimensional atlas of the nearby universe that had ever been created. Then came the Sloan Digital Sky Survey, beginning observations in the year 2000, eventually charting the positions and distances of millions of galaxies across billions of light-years of cosmic depth. Each successive survey peeled back another layer of structure, and each time the same unmistakable pattern emerged. Filaments threaded through space like the strands of an immense web. Walls of galaxies stretch for hundreds of millions of light-years in thin sheets. Dense clusters glowed at the intersections where multiple filaments converged, and between all of these luminous structures, filling the vast volumes in between, lay the voids. The Sloan survey produced some of the most stunning three-dimensional maps of the universe ever assembled. When you look at one of these maps, the first thing that strikes you is not the galaxies, it is the gaps. Bright points representing individual galaxies cluster along sinuous threads, forming a web-like lattice stretching in every direction across billions of light-years. But between those threads lie enormous dark bubbles where almost no galaxies exist. Some of these bubbles span hundreds of millions of light-years in diameter. They are not small irregularities in an otherwise smooth distribution. They are the dominant visual feature of the map. The impression is immediate and unmistakable. The universe has the texture of foam. Matter clings to thin surfaces and narrow channels, while the vast interior volumes remain hollow. Scientists formalize this architecture under the name cosmic web. It is the largest known structure in nature, extending across the entire observable universe and organizing all visible matter into 4 distinct components. The first component is nodes. These are the densest regions, the intersections where multiple filaments converge. Galaxy clusters form at these crossroads, packing hundreds or thousands of galaxies into relatively compact volumes spanning just a few million light-years. Nodes are the busiest neighborhoods in the cosmos, full of colliding galaxies, superheated gas glowing at temperatures of hundreds of millions of degrees, and supermassive black holes devouring matter at their centers. The second component is filaments. These are the threads of the web, elongated chains of galaxy groups stretching for hundreds of millions of light-years between nodes. Filaments channel matter from lower density regions toward the dense clusters at their endpoints, acting as cosmic supply lines that feed galaxy formation in the most crowded parts of the web. The third component is walls, also called sheets. These are broad, flat concentrations of galaxies that form where filaments meet along two-dimensional surfaces. Walls are thinner and more diffuse than filaments, but extend across truly enormous distances. Some of the largest coherent structures ever observed belong to this category. The Sloan Great Wall, identified in 2003, stretches approximately 1.4 billion light-years in length. And then there is the fourth component, the one that occupies more space than the other 3 combined, the voids. Voids are not merely gaps in the cosmic web, they are its defining feature. Consider what occupies the most volume in a sponge. It is not the solid material forming the walls and channels. It is the open space filling the pores. The same principle holds at cosmic scales. The filaments, walls, and nodes of the cosmic web contain nearly all the visible matter in the universe, but they occupy a minority of the total volume. The voids fill the rest, and the rest turns out to be almost everything. Quantifying this imbalance took decades of survey work and sophisticated statistical analysis. but modern measurements have converged on a figure that should permanently alter how you picture the cosmos. Voids occupy approximately 80 to 90% of the total volume of the observable universe. The filaments, walls, clusters, and superclusters that contain the overwhelming majority of galaxies, stars, gas, and dust are all packed into the remaining 10 to 20%. The universe is not a sea of galaxies with occasional gaps between them. It is a vast expanse of underdense space with thin threads of matter woven sparsely through it. This changes what you should see when you imagine the cosmos at its grandest scale. Every photograph of deep space, every Hubble ultra-deep field image packed with thousands of galaxies stretching back to the edge of observable time, every sweeping visualization showing clusters and superclusters reaching the limits of detection, all of those images capture the thin minority of the universe where matter happened to concentrate. They show you the threads and nodes of the cosmic web, the crowded, busy places where galaxies formed and evolved. But the overwhelming majority of cosmic volume lies between those images, in the regions between the filaments, in the enormous dark interiors of the bubbles. Those regions are almost never photographed because there is practically nothing there to photograph. If you could shade a cosmic map so that void regions appeared in one color and matter-rich structures in another, the map would be dominated by void. The filaments would resemble thin scratches across an otherwise featureless canvas. Mapping voids with precision requires enormous datasets and careful statistical analysis. Scientists identify voids by comparing the observed distribution of galaxies to the expected average density. They divide surveyed volumes into cells, count the galaxies in each cell, and search for contiguous regions where the count falls significantly below the cosmic mean. Various algorithms have been developed to automate this process, each defining void boundaries according to slightly different mathematical criteria, but they all converge on the same broad picture. One particularly valuable method is called void stacking. Individual voids vary in shape, size, and depth, which makes it difficult to study any single void's internal structure in fine detail. But by averaging the profiles of hundreds or thousands of voids together, aligning them by their centers, scientists can build a composite portrait of the typical void. This average profile reveals a characteristic structure. Voids are deepest at their centers, where the density reaches its minimum. Moving outward, density gradually rises until you reach the boundary called the compensation wall, a ridge of slightly above average density where matter swept outward by the void's expansion has accumulated against the surrounding web. The sizes of cosmic voids span a wide range. Small voids measure roughly 30 to 50 million light-years across. These are the most common type, scattered through the cosmic web like tiny air pockets in carbonated water, filling the spaces between neighboring galaxy groups. Medium voids stretch 100 to 300 million light-years in diameter. These are the standard building blocks of the cosmic foam, the characteristic bubbles that give the large-scale universe its distinctive texture. Then there are the supervoids, underdense regions exceeding 500 million light-years across. Supervoids are rarer and more challenging for standard cosmological models to produce. Generating one requires initial density fluctuations that were unusually smooth over enormous volumes, a condition the lambda cold dark matter model predicts should happen only infrequently. Each time observers discover a supervoid larger or deeper than simulations easily account for, it puts additional pressure on the theoretical framework. Computer simulations have become indispensable tools for understanding void formation. Scientists build virtual universes inside supercomputers, seeding them with the same initial conditions inferred from precise observations of the cosmic microwave background, and then running the gravitational clock forward for billions of simulated years. These simulations reliably produce cosmic webs that match reality remarkably well, complete with filaments, clusters, and voids arranged in patterns closely mirroring actual survey data. By tracking how simulated voids form, grow, and merge with neighboring voids over cosmic time, researchers can test and refine their understanding of the physics governing real cosmic structure. One key insight from simulations is that voids are not static features frozen into the fabric of the universe. They evolve continuously. In the early cosmos, when matter was distributed more evenly and density contrasts were still minuscule, voids were shallow and modest in extent. As gravitational instability amplified primordial density fluctuations over billions of years, overdense regions collapsed into filaments and clusters, while underdense regions expanded outward into voids. This process mirrored the growth of dense structures but in reverse. While clusters grew by accumulating matter, voids grew by losing it. The expansion of voids accelerated further as the universe aged and dark energy became the dominant component of cosmic energy over the last several billion years. In the current epoch, dark energy contributes roughly 68% of the total energy content of the universe, overwhelming the gravitational pull of matter across all but the densest regions. Today, voids are larger and emptier than at any previous epoch in cosmic history, and they continue growing with every passing billion years. The cosmic web is not a fixed, permanent architecture. It is a dynamic, evolving structure that becomes more extreme over time, its voids widening, its filaments slowly thinning, the contrast between full and empty growing sharper and sharper as dark energy tightens its grip on the cosmos. But simulations also revealed something troubling. While the standard model successfully reproduces the typical population of voids, it struggles with the largest and deepest ones. The biggest supervoids found in real sky surveys appear to exist at sizes and depths that simulations generate only rarely. Either the simulations are missing a piece of the physics, the observations contain systematic biases that overestimate void properties, or the initial conditions of the universe allowed for more extreme structures than the standard model readily accommodates. This tension between theory and observation became one of the defining puzzles in the study of cosmic large-scale structure. That puzzle intensified beyond anything astronomers had anticipated when they uncovered just how large the largest void could be. The Boötes void was 330 million light-years across and was considered extraordinary, a statistical anomaly straining the limits of standard structure formation theory. Subsequent surveys found other large voids scattered through the cosmos, some exceeding 500 million light-years in diameter. Each discovery raised the same persistent question: was this the biggest, or was something far larger waiting in the data, too vast and too diffuse for earlier surveys to resolve? The answer, when it finally emerged, was not just larger, it was so enormous that it redefined what astronomers believed a single cosmic structure could be. A void so vast that the Boötes void could fit inside it thousands of times over without making a measurable difference to its emptiness. A void so immense that entire superclusters, each containing hundreds of thousands of galaxies, reside within its boundaries, and yet the region still registers as profoundly underdense compared to the cosmic mean. The scale was not an incremental step up from previous discoveries. It was a leap into a category that many theorists had assumed could not exist. And the most unsettling part of that discovery was not its scale. It was not the sheer number of missing galaxies or the staggering volume of underdense space. It was something far more personal. It was where the void turned out to be located, and what that location meant for every measurement humanity has ever made about the cosmos. What makes the largest void so deeply disquieting is not what exists inside it. It is how much of the universe it occupies, and how it forces us to confront the possibility that the cosmos is shaped not by the matter we can see, but by the vast regions where that matter is absent. After the Boötes void entered the literature, astronomers began hunting for others. They did not have to look hard. Every new redshift survey that mapped a larger volume of the cosmos revealed more voids, some comparable in size to Boötes, others smaller, a few considerably larger. The cosmic web was turning out to be even more hollow than initial observations suggested. But the truly enormous voids, the ones that would eventually force a crisis in theoretical cosmology, announced themselves not through galaxy surveys at all. They announced themselves through ancient light, The cosmic microwave background is the oldest light in the universe. It was released approximately 380,000 years after the Big Bang, at the moment when the primordial plasma cooled enough for protons and electrons to combine into neutral hydrogen atoms for the first time. Before that moment, the universe was opaque. Photons bounced endlessly between charged particles, unable to travel any meaningful distance. When atoms formed, the photons were suddenly free. They streamed outward in every direction and have been travelling through the cosmos ever since, cooling as space expanded, their wavelengths stretching from the searing glow of a 3,000-degree plasma down to the faint microwave hum we detect today at a temperature of approximately 2.7 Kelvin, barely above absolute zero. This relic radiation fills the entire observable universe. It arrives from every direction in the sky, and its temperature is remarkably uniform. But that uniformity is not perfect. Tiny variations exist, typically only a few millionths of a degree warmer or cooler than the average. These minuscule temperature differences encode the density fluctuations that existed in the early universe, the seeds that gravity later amplified into the cosmic web of filaments and voids. Warmer spots correspond to regions that were slightly denser. Cooler spots correspond to regions that were slightly less dense. By mapping these temperature variations across the entire sky, satellites like the Cosmic Background Explorer, the Wilkinson Microwave Anisotropy Probe, and the Planck spacecraft created what amounts to a baby picture of the universe, a snapshot of conditions when the cosmos was less than 1% of its current age. In 2004, the Wilkinson Microwave Anisotropy Probe, commonly known as WMAP, produced the most detailed full-sky temperature map available at the time. When scientists examined this map, they noticed something peculiar. In the direction of the southern constellation Eridanus, there was an unusually cold patch. It was roughly 5 to 10 degrees across on the sky and approximately 70 millionths of a degree cooler than the surrounding cosmic microwave background temperature. That sounds vanishingly small. In everyday terms, 70 millionths of a degree is so tiny that no thermometer on Earth could distinguish it from zero variation. But in the context of the cosmic microwave background, where the typical temperature fluctuations measure only about 18 millionths of a degree from one spot to another, this cold patch was striking. It was significantly colder and substantially larger than the standard statistical models of the early universe easily predicted. Scientists calculated that a patch this cold and this large should occur in only about 1 to 2% of randomly generated universes based on the standard cosmological model. It was not impossible by any means, but it was uncommon enough to demand a careful investigation. Something had to explain it. Several explanations were proposed. Some researchers suggested it was simply a statistical fluke, a rare but unremarkable roll of the cosmic dice. Others speculated about more exotic possibilities, including the theoretical fingerprint of a collision between our universe and a neighbouring universe in a hypothetical multiverse. But the most physically grounded explanation came from a different direction entirely. What if the cold spot was not a relic of the early universe at all? What if something between us and the cosmic microwave background was causing the temperature drop? That something turned out to be an enormous void. When light from the cosmic microwave background travels through the universe on its way to our detectors, it does not arrive pristine and untouched. It must pass through 13.8 billion years of cosmic structure, through every filament, cluster, wall, and void that lies along the line of sight between the surface of last scattering and our instruments. Each of these structures leaves a subtle mark on the passing photons. Dense regions exert gravitational influence, tugging on light and altering its energy. Underdense regions exert far less gravitational pull, and the difference is measurable. This interaction produces an effect called the integrated Sachs-Wolfe effect, named after the physicists Rainer Sachs and Arthur Wolfe, who predicted it in 1967. The word integrated refers to the fact that the effect accumulates over the entire path the photon travels through a given structure, adding up the tiny energy changes along the way. Here is how it works. When a photon enters a gravitational potential well, such as the slight depression in space-time created by a concentration of matter, it gains energy. It blue shifts slightly, its wavelength compressing as it falls inward. When it exits the well, it loses energy, red shifting as it climbs back out. In a static universe, these two effects would cancel perfectly. The photon would emerge with exactly the same energy it had before entering. But the universe is not static. It is expanding, and that expansion is accelerating due to dark energy. During the time the photon spends traversing the gravitational well, the well itself changes. In a void, where dark energy dominates and gravity is weak, the void expands while the photon is passing through. The gravitational well becomes shallower. The photon loses more energy climbing out of the now shallower well than it gained falling in. It arrives at our detectors with slightly less energy than it would have had if the void were not there. Less energy means a longer wavelength. A longer wavelength means a lower temperature. The photon registers as cooler. For small voids, this effect is negligible. The energy loss is so tiny that it vanishes entirely in the noise of other temperature variations across the cosmic microwave background. But for an exceptionally large void spanning hundreds of millions or even billions of light years, the cumulative effect becomes detectable. The photon spends an enormously long time traversing the void, potentially millions of years, and during that entire transit, the void is expanding. The gravitational well becomes progressively shallower the entire time. By the time the photon exits, it has lost measurably more energy than it gained on the way in. That energy deficit translates directly into a temperature drop, and for the largest voids, that drop becomes visible against the otherwise uniform glow of the cosmic microwave background. Astronomers suspected that the WMAP cold spot might be caused by just such a void. In 2007, a team led by Lawrence Rudnick used radio survey data to search for an underdensity in the direction of the cold patch. They found suggestive evidence of a large void at a distance of roughly 6 to 10 billion light-years. But the data were noisy and the detection was debated vigorously for years, with some researchers arguing that the apparent underdensity was an artifact of incomplete survey coverage, and others insisting the signal was real. Not until further galaxy surveys probed that region of the sky with greater depth and better statistics did a clearer picture emerge. A substantial underdensity does appear to exist in the general direction of the Eridanus cold spot, a supervoid approximately 1.8 billion light-years across, with a density deficit of roughly 20 to 30% below the cosmic average. Whether this void is solely responsible for the full temperature anomaly of the cold spot remains an open question. Calculations suggest the integrated Sachs-Wolf effect from a void of that size and depth can account for perhaps half of the observed temperature deficit. The remainder may be a genuine primordial fluctuation from the early universe that happens to align with the void along the same line of sight. The combination of both effects, a real void in the foreground and a coincidental cold fluctuation in the background, may together explain the anomaly. Regardless of the cold spot debate, the Eridanus supervoid itself became one of the largest known structures of any kind. At approximately 1.8 billion light-years in diameter, it dwarfed everything previously catalogued in the void category. The Botes void, at 330 million light-years, would occupy a small corner of it, a modest underdensity nested within a far grander emptiness. The Eridanus supervoid demonstrated conclusively that the cosmos could produce underdense regions on scales that strained even the most generous theoretical expectations. But the Eridanus supervoid was not the end of the story. It was, in a sense, the warm-up act. In 2013, 3 astronomers published a paper that would quietly detonate one of the most significant findings in modern cosmology. Ryan Keenan, Amy Barger, and Lennox Cowie were not initially looking for a void. They were studying the distribution of galaxies in the local universe, mapping how galaxy number density varied with distance from Earth across multiple independent surveys. Their approach was careful, methodical, and deliberately conservative. They compiled data from several major galaxy catalogues spanning different wavelength bands, cross-referencing photometric surveys that estimated galaxy distances from their colors, with spectroscopic surveys that measured distances directly from redshifts. By combining these datasets, they could track how the density of galaxies changed as a function of distance outward from our position, testing whether the local universe matched the cosmic average or deviated from it. What they found was a pattern so consistent and so large that it took time to fully absorb. In every direction they looked, out to distances of approximately 1 billion light-years from Earth, the number of galaxies fell below the expected cosmic average, not by a trivial amount, not by a margin that could be dismissed as survey incompleteness or statistical noise. The deficit was roughly 20%. Everywhere around us, in every direction, for 1 billion light-years outward, 1 in 5 galaxies that should exist according to the cosmic average was simply not there. The shortfall appeared in each survey independently. It appeared in infrared data and in optical data. It appeared whether the team used photometric estimates or spectroscopic measurements. The signal was stubborn and it was everywhere. The pattern formed a sphere, a colossal underdense bubble centered approximately on our position in the universe, extending outward for roughly 1 billion light-years in radius, making the full structure approximately 2 billion light-years across. The team named it the KBC Void, using their initials, and it immediately became the largest confirmed cosmic void ever observed. The KBC Void is not easy to comprehend. 2 billion light-years is not a number the human mind can process as a distance. It is a number that requires scaffolding to even approach. Consider first that light, the fastest thing in the universe, travels at approximately 186,000 miles per second. In a single year, light covers roughly 6 trillion miles. Multiply that by 2 billion. The diameter of the KBC void is approximately 12 sextillion miles. Written out, that number has 22 digits. But those digits remain abstract. They do not convey the experience of crossing such a distance, because no human experience maps onto it. So let us try a different approach. The Milky Way galaxy, our home, is roughly 100,000 light-years across. It is enormous by any human standard. It takes light 100,000 years to cross it, a duration that encompasses the entire span of modern human existence several times over. Now consider what it would take to line up Milky Way galaxies side by side to span the KBC void. You would need 20,000 of them, laid edge to edge in a row, each one a spiral containing hundreds of billions of stars, to stretch from one side of this void to the other, 20,000 galaxies wide. That is the emptiness we are sitting inside. Or consider it from the perspective of the nearest large galaxy. Andromeda lies approximately 2.5 million light-years from the Milky Way. It is the farthest object most humans can see with the unaided eye, a faint smudge of light visible on clear autumn nights. The distance to Andromeda is considered one of the great chasms in our local cosmos. You could fit approximately 800 of those chasms, 800 trips from the Milky Way to Andromeda, laid end to end, inside the KBC void. That is how large this structure is. 800 Andromeda distances across, and almost none of those distances contain anything close to the expected amount of matter. The existence of the KBC void raised an immediate and uncomfortable question. If this void is so large, why did it take until 2013 to find it? The answer lies in one of the most fundamental difficulties in observational astronomy. We are inside the void. Detecting a structure you are embedded within is extraordinarily difficult because you have no external reference point from which to see the whole thing. It is like trying to determine the size of a valley while standing at its bottom. You can see the slopes rising around you, but you cannot easily tell where the valley ends and the next ridge begins without climbing out of it first. Astronomers had to infer the void's existence not by seeing it from outside, but by counting galaxies at progressively greater distances and noticing that the counts were consistently too low compared to the cosmic average. The void revealed itself not as a visible absence on a map, but as a persistent statistical shortfall that showed up in survey after survey. Multiple independent analyses have since confirmed the KBC void's existence. Different research teams using different galaxy catalogues, different survey methodologies, and different portions of the sky have all found the same basic result. The local universe, out to about 1 billion light-years in every direction, is underdense by approximately 15 to 25%. The exact depth and extent vary slightly depending on the survey used and the method of analysis, but the central finding remains robust. We live inside a very large hole in the distribution of cosmic matter. The implications of this location are vast, and they reach into the most precise measurements cosmologists have ever attempted. But first, it is worth pausing to appreciate what it means for familiar astronomical structures to exist within this void. Our galaxy, the Milky Way, is part of the Local Group, a collection of roughly 80 galaxies, including our large neighbour Andromeda. The Local Group is itself embedded within the Laniakea supercluster, a gravitational basin containing approximately 100,000 galaxies spread across 520 million light-years. Laniakea is enormous. It is one of the largest coherent gravitational structures in the mapped universe. Galaxies within Laniakea are not merely drifting in proximity, they are flowing together, pulled toward a common gravitational center called the Great Attractor, moving in coordinated streams that have been measured and mapped by tracking the peculiar velocities of thousands of individual galaxies. Laniakea, with all its 100,000 galaxies, its thousands of galaxy groups, its dozens of major clusters, its 520 million light-years of gravitationally linked structure, fits inside the KBC void. Not just barely. The void is roughly 4 times wider than Laniakea. You could place several Laniakea-sized superclusters side by side within the void's volume and the region would still register as underdense. This is what makes the KBC void so conceptually jarring. It is not empty in the way a room with no furniture is empty. It contains real structure, enormous structure that by any ordinary standard would be considered impressively dense and complex. It contains superclusters and galaxy clusters and spiral galaxies, and billions upon billions of individual stars burning through their nuclear fuel. But measured against the cosmic average, against what the same volume of space elsewhere in the universe would contain, all of that impressive structure falls short. The matter is there, but not enough of it. The galaxies exist, but too few of them. The cosmic ledger is unbalanced by roughly 20%, and that deficit extends in every direction for 1 billion light-years. This is the distinction that separates a cosmic void from naive emptiness. The Botes void, with its 60 scattered galaxies across 330 million light-years, approaches something closer to genuine desolation. But the KBC void, with its superclusters and galaxy clusters and billions of individual stars, is underdense. It is a region where the cosmic ledger does not balance. Matter should be distributed at a certain average density across the universe, and in this region it falls measurably short. The deficit matters because it is large enough to influence how the universe behaves within the void's boundaries. A 20% shortfall in matter density translates to a 20% shortfall in gravitational pull. Less gravity means less resistance to cosmic expansion. Less resistance means space within the void stretches faster than space in regions where matter is closer to the cosmic average. This difference in expansion rate is not hypothetical. It is measurable, and it has consequences that reach directly into the most precise measurements cosmologists have ever attempted. But before we reach those consequences, it is worth considering how the KBC void compares to the Eridanus supervoid and to the Boötes void, because the comparison illuminates something important about the hierarchy of cosmic emptiness. The Boötes void, discovered in 1981, measures approximately 330 million light-years across with an extremely deep density deficit. It is one of the emptiest regions ever found, relative to its size, containing almost no galaxies where thousands should exist. It is a concentrated pocket of cosmic desolation. The Eridanus supervoid, identified through its imprint on the cosmic microwave background, stretches roughly 1.8 billion light-years in diameter, with a density deficit of approximately 20 to 30%. It is larger than Boötes by a factor of more than 5, but somewhat less empty in relative terms. And then there is the KBC void, approximately 2 billion light-years across with a density deficit of roughly 20%. It is the largest of the three by physical extent, though not necessarily the deepest in relative underdensity. What these three structures represent is a spectrum of cosmic emptiness. Boötes is small and deep, a concentrated pocket of extreme desolation where almost no galaxies survive. Eridanus is vast and moderately deep, an enormous underdensity that leaves a measurable scar on the oldest light in the universe. The KBC void is the most expansive of all, a structure so large that it encompasses our entire observable local universe and extends far beyond the boundaries of any structure humanity has ever called home. Among these three, the KBC void holds the distinction of being the largest confirmed cosmic void by sheer physical scale. That designation carries weight not because size alone is impressive, but because the physics that operates within such a large underdensity has real, measurable effects on the observable universe. The larger the void, the more profoundly it influences the behavior of matter, energy, and light within its boundaries. And it is those effects that push the KBC void from an interesting astronomical curiosity into something far more consequential. A 20% matter deficit spread across 2 billion light-years is not a passive feature of the cosmic landscape. It is an active influence on the forces that shape the universe around us. Inside the void, dark energy faces less gravitational opposition. Galaxies experience less gravitational pull from surrounding matter. Light passing through the void behaves differently than light traveling through denser regions. Every measurement we make of the cosmos, from the expansion rate of the universe to the age we assign to distant objects, passes through the lens of this void. The statistical rarity of the KBC void adds another layer of unease. Standard cosmological simulations based on the lambda cold dark matter model produce voids that generally match the observed population at smaller and medium scales. But producing a void as large and as deep as the KBC void is genuinely rare in these simulations. When researchers generate thousands of simulated universes and search each one for voids matching the KBC's dimensions and density deficit, they find very few matches. Some analyses have estimated that a structure this extreme represents a deviation of several sigma from the expected density distribution, meaning it lies far out on the tail of the probability curve. In statistical terms, a 3 sigma event has roughly a 1 in 700 chance of occurring. A 5 sigma event has less than a 1 in a million chance. The KBC void, depending on the analysis, falls somewhere in this range or potentially beyond it. The universe can produce such structures through the normal amplification of primordial density fluctuations, but the probability is low. Finding ourselves inside one, therefore, raises the uncomfortable question of whether we occupy an unusually atypical region of the cosmos, whether we have been extraordinarily unlucky in the cosmic lottery of location, or whether the theoretical models that define what counts as typical are themselves incomplete or flawed in ways we have not yet recognized. This question connects directly to the cosmological principle, the foundational assumption that the universe is homogeneous and isotropic at sufficiently large scales. The cosmological principle is not a minor technical detail. It is the bedrock upon which nearly all of modern cosmology is constructed. The equations that describe cosmic expansion, the models that predict structure formation, the calculations that determine the age and composition of the universe, all of them depend on the assumption that no location in the cosmos is fundamentally special. A void 2 billion light-years across with a 20% density deficit is a significant inhomogeneity. It is not a small wrinkle in an otherwise smooth fabric. It is a major feature occupying a substantial fraction of the nearby observable universe. And our position near its center means our view of the cosmos in every direction is filtered through this underdensity. If the cosmological principle holds, our location should not matter for the large-scale measurements we make. The universe should yield the same expansion rate, the same matter density, the same fundamental parameters whether measured from inside the void or from outside it. but the void's gravitational influence creates local conditions that differ measurably from the cosmic average, which introduces the troubling possibility that our measurements reflect not universal properties, but local ones, distorted by the particular emptiness that surrounds us. This tension between the assumption of cosmic uniformity and the reality of local underdensity is one of the most active debates in modern cosmology. The KBC void sits squarely at the center of that debate, a structure so large that it tests the very framework scientists use to interpret the universe. The question that follows is not merely academic. It reaches into the machinery of cosmic measurement itself. If we live inside a void that alters the local expansion rate, alters the velocity of nearby galaxies, alters the gravitational environment through which light travels to our telescopes, then the numbers we extract from our most precise observations may carry a systematic bias that we are only beginning to understand. The void does not just surround us passively, it actively shapes what we see. And what we see, filtered through 2 billion light-years of underdense space, may not be the whole truth about the cosmos. The void warps the physics within it, bends the ancient light passing through it, fundamentally changes the galaxies trapped inside it, and may be responsible for one of the most stubborn and consequential contradictions in the history of modern science. The KBC void does not merely surround us. It filters every photon that reaches our telescopes, biases every distance we have ever measured, and inflates every velocity we have ever recorded. We did not discover this void by looking outward. We discovered it by realizing that the numbers coming back had never been quite right. Gravity inside a cosmic void does something that sounds impossible. It pushes outward, not because the force of gravity has reversed. Gravity always attracts mass toward mass. That has not changed. But the geometry of a void creates a situation where the net effect of gravity on anything inside it is a pull toward the edges and away from the center. The reason is straightforward once you picture it correctly. All the matter, the dense filaments and galaxy clusters and walls of the cosmic web, lies outside the void. Inside the void, matter is scarce. So the gravitational pull on any galaxy sitting within the void comes predominantly from the denser regions beyond its boundaries. That pull is directed outward, toward the walls, toward the filaments, toward everywhere the matter actually is. The result is an outflow. Galaxies inside a void do not sit passively in place. They accelerate outward from the void's center, driven by the gravitational imbalance between the sparse interior and the dense exterior. This outflow is not subtle. It is measurable, consistent, and significant. Astronomers can track galaxy velocities using a combination of redshift measurements and independent distance estimates. Redshift tells you how fast a galaxy appears to be receding, but that recession velocity is a blend of two separate motions layered on top of each other. One is the expansion of space itself, the smooth, universal stretching of the cosmos that carries all galaxies apart from one another at a rate proportional to their separation distance. This component is called the Hubble flow. The other is the peculiar velocity of the galaxy, its actual motion through local space caused by gravitational forces from nearby structures. Every galaxy has both components simultaneously. A galaxy's observed redshift is the sum of the two, and disentangling them from a single measurement is one of the most persistent challenges in observational cosmology. In most regions of the universe, peculiar velocities are modest and random in direction. For every galaxy being pulled toward a cluster on one side, another galaxy is being pulled toward a different cluster on the opposite side. When you average over large volumes, the peculiar velocities tend to cancel out, leaving only the clean signal of cosmic expansion. Inside a void, this cancellation breaks down. The peculiar velocities all point the same way, outward. Every galaxy within the void feels the same gravitational imbalance, pulling it toward the denser regions beyond the void's edge. This creates a systematic, coherent outflow that adds velocity on top of the cosmic expansion. When astronomers measure the redshift of a galaxy inside the void, they are seeing the real cosmic expansion plus the outflow velocity stacked on top of it. The galaxy appears to be receding faster than it actually is due to expansion alone. This distinction matters enormously, because the number we use to describe how fast the universe expands depends on separating these two contributions cleanly. And inside a void, the separation becomes treacherous. The Milky Way participates in this outflow. Our galaxy is moving away from the center of the nearby local void, a smaller underdense region adjacent to the larger KBC void at approximately 600,000 miles per hour. This velocity is not caused by the expansion of space. It is a peculiar velocity driven entirely by the gravitational deficit of the void. The denser structures beyond the void, including the Virgo cluster and the broader Laniakea flow toward the Great Attractor, are pulling us outward. Meanwhile, the void behind us contributes nothing to counteract that pull because it contains almost no matter to pull us back. The result is a galaxy in motion, hurtling through space at a speed that dwarfs any velocity humans have ever achieved with a spacecraft. But the local void is small compared to the KBC void. The outflow pattern of the KBC void operates on a vastly larger scale. Galaxies hundreds of millions of light years from our position show the same pattern. They are moving outward from the void's center faster than cosmic expansion alone predicts. Measurements of these bulk flows, large-scale coherent motions of galaxies across enormous volumes, consistently exceed the predictions of standard cosmological models that assume a smooth, uniform universe. The flows extend outward for at least 200 to 300 million light-years and reach velocities of 400 kilometers per second or more. Standard lambda cold dark matter simulations struggle to produce bulk flows this strong at these scales. The universe appears to be more structured, more dynamic, and more gravitationally unbalanced in our region than the models comfortably predict. These bulk flows carry the fingerprint of the void. When researchers model what the velocity field should look like if a void of the KBC's dimensions and depth exists around us, the predicted flows match the observed ones remarkably well. The magnitude, the direction, the way the flow strength varies with distance from the void center, all of it lines up. This agreement provides some of the strongest independent evidence that the KBC void is real, and that it actively shapes the motions of galaxies across billions of light-years of space. This brings us to the crisis at the heart of modern cosmology. The Hubble constant is the number that quantifies how fast the universe expands. It tells you that for every megaparsec of distance, roughly 3.26 million light-years, space expands at a certain velocity measured in kilometers per second. Measure the Hubble constant accurately, and you know the expansion rate of the entire cosmos. From the expansion rate, you can calculate the age of the universe, the density of dark energy, the curvature of space-time, the ratio of matter to radiation, and the future trajectory of cosmic evolution. Nearly everything in cosmology connects back to this single number. It is the heartbeat of the universe reduced to a measurement, and for decades, getting it right has been one of the central ambitions of the field. The problem is that two independent and highly precise methods of measuring the Hubble constant produce two different answers, and neither one is wrong. The first method looks at the ancient universe. Scientists study the cosmic microwave background, the relic radiation from 380,000 years after the Big Bang. This light encodes detailed information about the density, temperature, and expansion rate of the early cosmos. By feeding this data into the standard cosmological model, researchers can calculate what the expansion rate should be today. The Planck satellite performed this measurement with extraordinary precision. The answer? Approximately 67 kilometers per second per megaparsec. The second method looks at the nearby universe. Astronomers observe objects with known intrinsic brightness, particularly Type Ia supernovae and Cepheid variable stars. These objects serve as cosmic measuring sticks. Because scientists understand how bright they truly are, they can compare that intrinsic brightness to the apparent brightness as seen from Earth and calculate the distance. Combine the distance with the redshift, and you get the expansion rate directly, measured locally rather than inferred from the early universe. Multiple teams using this approach, most notably the SH0ES collaboration led by Adam Rees, consistently measure a higher value, approximately 73 kilometers per second per megaparsec. The difference is roughly 9%. That might sound small, almost negligible in everyday terms, but both measurements carry very small error bars, the product of decades of refined technique and millions of dollars of dedicated observation time. The disagreement has reached what statisticians call 5 sigma significance, meaning there is less than a 1 in a million probability that the discrepancy is due to random chance alone. In particle physics, 5 sigma is the gold standard for declaring a discovery. In cosmology, it signals a genuine conflict between two ways of understanding the same universe. Both numbers are almost certainly correct measurements of what they are measuring. They simply are not measuring the same thing. This discrepancy is called the Hubble tension, and it has consumed cosmology for more than a decade. Dozens of proposed solutions have been put forward. Some invoke new physics in the early universe, an extra burst of expansion shortly after the Big Bang that would change the predicted present-day rate. Others propose modifications to dark energy, suggesting it evolves over time rather than remaining constant. Still others suggest systematic errors lurking in the measurement techniques, perhaps dust-dimming supernovae more than expected, or Cepheid calibrations varying between galactic environments. Each proposed solution has been scrutinized and most have been found wanting. The tension persists. The KBC void offers a different kind of explanation. It does not require new particles. It does not require modifying gravity or inventing new forces. It requires only accepting that we live in an atypical region of the cosmos and that this location biases our local measurements. Here is how it works. The cosmic microwave background measurement probes the expansion rate of the entire universe averaged over the full history of cosmic evolution. It is a global measurement. It sees through the void and beyond it, sampling conditions across the entire observable cosmos. The number it produces, 67 kilometers per second per megaparsec, reflects the true average expansion rate of the universe. The local measurement, the one using supernovae and Cepheids, probes the expansion rate within our cosmic neighborhood, and our cosmic neighborhood is the interior of the KBC void. Within the void, the outflow velocity field adds extra recession speed to every galaxy we observe. Galaxies are not just being carried apart by cosmic expansion. They are also being pushed outward by the gravitational imbalance of the void. When we measure their redshifts, we capture both motions combined. The result is a local expansion rate that appears higher than the global average. We are not measuring the universe's true expansion rate with our nearby supernovae. We are measuring the expansion rate plus the void's outflow and interpreting the sum as if it were expansion alone. The magnitude of this effect has been modelled carefully. A void approximately 2 billion light-years across with a 20% density deficit produces an outflow that boosts the apparent local Hubble constant by roughly the amount needed to bridge the gap between 67 73. The match is not perfect, and different analyses yield slightly different estimates depending on the assumed void profile. But the order of magnitude is right, and the direction is right. The void makes the local expansion appear faster, which is exactly what the observations show. If the void hypothesis is correct, the Hubble tension is not a sign of broken physics, it is a sign of broken assumptions. We assumed our location was typical. We assumed local measurements reflected global properties. Those assumptions may be wrong. The implication is that much of our cosmological framework, while mathematically rigorous and internally consistent, may rest on a foundation that does not account for the unusual emptiness of our immediate cosmic environment. The consequences ripple outward from the Hubble constant into other measurements. If the local expansion rate is inflated by the void, then calculations that use the higher value to estimate the age of the universe will produce an age that is too young. The cosmic microwave background measurement gives a universe approximately 13.8 billion years old. The higher local Hubble constant, if taken at face value as a global number, would make the universe closer to 12.7 billion years old. That younger age creates immediate conflicts. The oldest known stars, found in globular clusters in the Milky Way's halo, have ages estimated at approximately 13 billion years based on well-tested models of stellar evolution. A universe, only 12.7 billion years old, cannot contain stars that are 13 billion years old. The numbers collide. If the void hypothesis resolves the Hubble tension by attributing the higher local value to outflow rather than true expansion, this age paradox vanishes. The universe is 13.8 billion years old. The stars fit comfortably within that timeline, and the apparent disagreement was an artifact of our location all along. But the void does more than bias expansion measurements. It fundamentally alters the environment in which galaxies form and evolve, creating conditions that differ sharply from those in the dense filaments and clusters of the cosmic web. Galaxies inside cosmic voids grow up in isolation. In dense regions, galaxies live crowded lives. They pass near neighbors frequently. Gravitational interactions strip gas from their outer regions. Collisions and mergers trigger violent bursts of star formation that consume available fuel rapidly. Close encounters with massive neighbors distort their shapes, warp their spiral arms, and funnel material toward their central supermassive black holes. Over billions of years, these interactions transform galaxies. Spiral galaxies merge into elliptical galaxies. Star-forming galaxies exhaust their gas and become passive, red, and quiet. The dense environment accelerates evolution, pushing galaxies through their life cycles faster. Void galaxies experience almost none of this. The distances between neighbors are so vast that gravitational interactions are rare. Mergers happen infrequently, if at all. Without the external triggers that drive rapid evolution in dense environments, void galaxies develop at their own pace, governed almost entirely by internal processes rather than environmental forces. The result is a population of galaxies that looks fundamentally different from what you find in filaments and clusters. Void galaxies tend to be smaller and less massive than their counterparts in dense regions. Most are classified as late-type systems, spirals and irregulars, rather than the elliptical galaxies that dominate cluster cores. Their morphologies are often strikingly undisturbed, with smooth disk profiles and regular rotation curves that show no sign of the gravitational battering common in crowded environments. They are galactic specimens preserved in near-pristine condition, largely untouched by the violent interactions that reshape galaxies elsewhere. One of the most distinctive features of void galaxies is their gas content. In dense regions, multiple processes conspire to remove gas from galaxies over billions of years of environmental exposure. Ram pressure stripping occurs when a galaxy moves through hot intracluster gas at high speed, which pushes cold hydrogen out of the galaxy like wind stripping leaves from a tree in a storm. Tidal interactions during close gravitational encounters pull gas out into long streams that stretch between passing galaxies and eventually disperse into the intergalactic medium. Starvation, a subtler process, occurs when the hot gas halo surrounding a galaxy is removed by the cluster environment, cutting off the supply of fresh cold gas that would otherwise have cooled and fallen onto the galaxy's disk to fuel future star formation. Even the intense radiation and energetic jets from nearby active galactic nuclei can heat surrounding gas and prevent it from cooling and collapsing into new stars, a mechanism known as feedback. Inside voids, none of these mechanisms operate effectively. Void galaxies retain their gas. They hold onto enormous reservoirs of neutral hydrogen that have never been compressed into stars, never stripped away by interactions, never heated beyond the point of collapse by external radiation. Many void galaxies are among the most gas-rich systems known, containing proportionally more raw fuel for star formation than comparable galaxies in dense environments. This gas richness creates a paradox. Void galaxies have more fuel for star formation, yet their overall star formation rates tend to be lower than in dense regions. The explanation lies in the conditions required to trigger star formation. Gas does not spontaneously collapse into stars. It needs a push, a compression event that raises the local density above the threshold for gravitational collapse. In dense environments, those pushes come from galaxy interactions, mergers, shockwaves from nearby supernovae cascading through the intergalactic medium, and tidal compressions from passing neighbours. In voids, those triggers are largely absent. The gas sits in extended reservoirs, stable and undisturbed, waiting for a compression event that may never come. Star formation proceeds, but slowly, driven by internal processes like spiral density waves rather than external violence. However, when star formation does ignite in void galaxies, it can be intense. Because the gas reservoirs are so large, any event that manages to compress a significant portion of the gas can produce a starburst, a short-lived period of extremely rapid star formation. Some void galaxies exhibit starburst activity that rivals anything seen in dense environments fueled by the enormous untapped gas supply. These bursts are typically triggered by internal instabilities rather than external interactions, making them qualitatively different from the merger-driven starbursts common in galaxy clusters. The chemical composition of void galaxies provides yet another window into their isolated and unhurried evolution. Stars create heavy elements through nuclear fusion and distribute them into the surrounding gas when they die. Over successive generations, a galaxy's gas becomes progressively enriched with heavier elements, a process called chemical evolution. Void galaxies, with their slower star formation rates, have produced fewer generations of stars and consequently exhibit lower metallicities, meaning their gas contains fewer elements heavier than helium compared to galaxies in dense regions. This lower metal content confirms that void galaxies have been evolving more slowly, processing their raw material into stars and heavy elements at a more leisurely pace than galaxies in the busy highways of the cosmic web. The dark matter halos surrounding void galaxies differ from those in dense environments as well. Every galaxy sits at the center of a much larger halo of dark matter, an invisible gravitational scaffold that extends far beyond the visible stars and gas. In dense regions, dark matter halos are subject to constant gravitational harassment from neighboring halos. They get stretched, distorted, and truncated by tidal forces. In voids, halos remain more spherical and undisturbed, preserving their shape over billions of years without the external forces that deform halos in clusters. This makes void galaxy halos cleaner subjects for testing theories of dark matter behavior, since their structure is governed almost entirely by the properties of dark matter itself, rather than by environmental complications. The study of void galaxies has transformed these underdense regions from astronomical backwaters into valuable scientific laboratories. By comparing how galaxies evolve in voids versus in dense environments, scientists can separate the effects of nature from nurture in galaxy evolution. Which properties of a galaxy are determined by its internal physics, its mass, its gas content, its rotation, and which are imposed by the external environment, the frequency of interactions, the density of surrounding matter, the proximity to other large structures. Void galaxies provide the control group, the baseline case of a galaxy developing in near total isolation. Every difference between a void galaxy and a cluster galaxy points to an environmental effect, a way that the surrounding cosmos shapes the objects within it. This laboratory function extends beyond individual galaxies to the fundamental physics of the universe. Cosmic voids are the only regions where dark energy dominates completely. In galaxy clusters, gravity is strong enough to hold structures together against the outward push of cosmic expansion. In filaments, gravity still exerts meaningful resistance. But inside voids, where matter is sparse and gravitational forces are feeble, dark energy controls the dynamics almost without opposition. Voids expand faster than the cosmic average precisely because dark energy encounters so little gravitational resistance within them. This makes voids natural testing grounds for measuring the properties of dark energy. Dark energy remains one of the deepest mysteries in physics. Discovered in 1998 through observations of distant Type Ia supernovae, it constitutes approximately 68% of the total energy content of the universe. It behaves oppositely to matter and gravity, pushing space apart rather than pulling it together, accelerating cosmic expansion rather than decelerating it, but its fundamental nature remains unknown. It could be a cosmological constant, an unchanging energy density woven into the fabric of space-time itself. It could be a dynamic field that varies in strength over time and space. Distinguishing between these possibilities requires precise measurements of how expansion accelerates in different environments and at different epochs in cosmic history. Voids provide a cleaner signal for these measurements than any other cosmic environment. In dense regions, the gravitational influence of nearby masses contaminates the expansion signal, making it difficult to isolate the contribution of dark energy. Inside voids, those gravitational complications are minimized. Galaxies move almost entirely under the influence of cosmic expansion and dark energy. By measuring how void galaxies move relative to the void edges, how fast voids expand over cosmic time, and how the shapes of voids change as the universe ages, scientists can probe dark energy's properties with reduced systematic contamination. The shape of voids carries particular diagnostic power. If dark energy is truly uniform, a cosmological constant identical everywhere in space and time, then voids should expand equally in all directions, remaining roughly spherical as they grow. But if dark energy has spatial variations, or if it evolves over time, voids might expand asymmetrically, becoming elongated or distorted in ways that betray the underlying physics. Observations of void shapes at different cosmic epochs can therefore test whether dark energy is the simple cosmological constant that current models assume, or something more complex and dynamic. Current measurements indicate that dark energy has been approximately constant over the last several billion years, consistent with the simplest models. But the uncertainties remain large enough that more exotic behavior cannot be ruled out. Future surveys from missions like the Euclid Space Telescope and the Vera C. Rubin Observatory will map thousands of voids at various distances, each providing an independent measurement of dark energy's influence. The KBC void, being the largest and nearest supervoid, offers the most detailed laboratory available. Its proximity allows measurements at a level of precision impossible for distant voids, making it a cornerstone of upcoming dark energy research. The physics inside the void also affects observations we make of objects far beyond its boundaries. Light from distant galaxies, supernovae, and quasars must travel through the KBC void on its way to our telescopes. As that light traverses the underdense region, it interacts with the void's gravitational field and expansion rate. The cumulative effect modifies the light's wavelength and energy in ways that influence how we interpret its source. Baryon acoustic oscillations, the frozen sound waves from the early universe that serve as cosmic rulers for measuring distances, show slight discrepancies when measured within the void, compared to measurements made at distances well beyond the void's edge. These discrepancies are consistent with the void inflating our local measurement of the expansion rate, providing yet another independent line of evidence that our cosmic environment systematically biases our observations. Every year the case builds. Bulk flow measurements match void predictions. The Hubble tension aligns with the expected outflow bias. Baryon acoustic oscillations show the predicted local discrepancy. Void galaxy populations confirm the expected evolutionary differences. The KBC void is not a single anomalous observation. It is a coherent framework that explains multiple otherwise puzzling features of the nearby cosmos. Whether this framework ultimately proves complete, or whether additional physics is needed to fully resolve the tensions in cosmology, remains an open question. But the void itself is no longer in doubt. The question that remains is not whether the void exists, or whether it affects our measurements. The question is what the existence of such a vast underdensity, combined with the dominance of voids throughout the cosmic web, tells us about the fundamental nature of the universe. If voids occupy 80 to 90% of cosmic volume, if the largest of them stretches 2 billion light-years across our own position, and if these structures are growing larger with every passing epoch, then the cosmos we inhabit is not defined by the galaxies and stars we celebrate, it is defined by the spaces between them. And those spaces have something to say about where the universe came from and where it is going. The void does not merely exist around us. It has shaped the galaxies within it, bent the light passing through it, and skewed the expansion rate we measure from inside it. Every observation we make carries its fingerprint, and the question that remains is no longer whether the void matters. It is whether the universe can be understood at all without accounting for the vast regions where almost nothing resides. There is a tendency, when confronting the scale of cosmic voids, to treat them as features of the universe, as if the universe is the primary thing and voids are secondary, holes punched in an otherwise complete fabric, as if the cosmos is fundamentally a place of matter and energy and structure, and voids are merely the leftover spaces where those things ran out. That framing is natural. It is also backwards. Consider the arithmetic of the observable universe. The observable cosmos, the sphere of space from which light has had time to reach Earth since the Big Bang, extends approximately 46 billion light-years in every direction. That is the stage on which all of cosmic history plays out. Every galaxy we have ever observed, every star whose light has ever registered on a detector, every atom of hydrogen and helium and carbon and iron that has participated in the 14 billion year story of cosmic evolution, all of it is contained within this volume. Now divide that volume according to how matter actually distributes itself. The filaments, walls, clusters, and superclusters of the cosmic web, the structures that contain essentially all the visible matter in existence, occupy between 10 and 20% of that total volume. Everything else, the remaining 80 to 90%, belongs to the voids. This figure has been stated before, but its meaning has not been absorbed. A number can be stated without being understood, and the meaning of this particular number has implications that most people, including many scientists, have not fully absorbed. What it means is that if you could drop a pin at a random location in the observable universe, chosen with perfect mathematical randomness, with no bias toward galaxies or clusters or any visible structure, the overwhelming probability is that the pin would land in a void, not near a galaxy, not close to a filament, not in the gravitational neighborhood of any significant structure. It would land in a region of space so underdense that the nearest substantial galaxy might lie hundreds of millions of light-years away in every direction. You would be surrounded by a darkness so vast and so sparse that the universe would appear, for all practical purposes, empty. This is not the exceptional outcome. This is the typical one. The voids are not the exception to the rule of cosmic structure. They are the rule. The galaxies are the exception. This inversion of perspective is difficult to internalize because every image of the cosmos we have ever produced emphasizes the opposite view. Telescopes are built to collect light. Cameras are pointed at things that shine. Survey maps highlight the positions of galaxies because galaxies are what the instruments detect. The entire history of astronomy has been a progressive deepening of our ability to find bright objects in the dark. Every advance in telescope technology, from Galileo's first refractor to the James Webb Space Telescope, has been an advance in light-gathering power, in sensitivity to faint sources, in the ability to resolve ever more distant and ever more ancient luminous objects. The resulting images create an overwhelming visual impression of abundance. The Hubble Deep Field, perhaps the most famous astronomical photograph ever taken, shows approximately 10,000 galaxies crammed into a patch of sky no larger than a grain of sand, held at arm's length. It suggests a universe overflowing with structure, bursting with matter, packed to the very edges with luminous objects competing for space in the frame. But that photograph is a profound selection effect. It shows only the places where light originates. It cannot show you the vastly larger volumes between those places where almost nothing exists and almost nothing shines. If you could somehow create an image that gave equal visual weight to every cubic megaparsec of space in the observable universe, including the voids, the galaxies would not dominate the frame. They would be barely visible, faint specks scattered across an overwhelming field of black that would stretch to every edge of the image without interruption. The origins of this architecture reach back to the earliest moment the universe permits us to examine. Within the first fraction of a second after the Big Bang, the cosmos underwent a period of explosive expansion called inflation. During this epoch, which lasted for an almost inconceivably brief interval, perhaps 10 to the negative 36 seconds or less, the observable universe expanded by a factor of at least 10 to the 26th power, space ballooned so rapidly that regions which had been in direct contact, close enough to exchange energy and information, were flung apart to distances that would take billions of years for light to cross. Inflation solved several deep puzzles in cosmology, explaining why the universe appears so geometrically flat, why the cosmic microwave background is so uniform in temperature, and why magnetic monopoles predicted by particle physics have never been observed. But inflation also did something else, something that would echo across the entire future history of the cosmos. It took quantum fluctuations and stretched them to macroscopic scales. Quantum mechanics dictates that the vacuum of space is not truly empty, even in a perfect void with no particles and no radiation. At the smallest conceivable scales, energy fluctuates. Virtual particles wink in and out of existence in pairs, borrowing energy from the vacuum for intervals so brief that the uncertainty principle prevents their detection as individual events. Fields jitter and oscillate around their ground states. The electromagnetic field, the Higgs field, all the quantum fields that permeate reality vibrate with a ceaseless, irreducible tremor. These fluctuations are fantastically small, operating at scales trillions of times smaller than an atomic nucleus. Under normal circumstances, at any scale relevant to atoms, molecules, planets, or stars, they average out to nothing. They are the background static of reality, always present but never consequential for anything larger than a subatomic particle. Inflation changed that in the most dramatic way imaginable. During those first fractions of a second, the exponential expansion of space grabbed these quantum fluctuations and stretched them across distances that would eventually span millions and billions of light years. A fluctuation that began smaller than a proton was inflated to a size larger than a future galaxy cluster. A fluctuation that represented a minuscule excess of energy in a volume smaller than an electron became a seed that would grow, over billions of years, into a filament containing millions of galaxies. A fluctuation that represented a minuscule deficit became a seed that would grow into a void spanning hundreds of millions of light years. The stretching was so thorough and so rapid that by the time inflation ended, the fluctuations were frozen in place, imprinted onto the fabric of space as permanent variations in energy density. Some regions ended up with infinitesimally more energy than the cosmic average. Others ended up with infinitesimally less. The differences were extraordinarily tiny, roughly 1 part in 100,000 from the mean, so small that they would be invisible to any conceivable measurement for hundreds of millions of years afterward. But they were real, they were permanent, and gravity, the most patient force in nature, would spend the next 14 billion years amplifying them into the grandest structures the cosmos has ever produced. In the regions that started with slightly more density than the cosmic average, gravity gained an early advantage. A little more matter meant a little more gravitational pull, which attracted a little more matter from the surroundings, which increased the gravitational pull further. This feedback loop operated with extraordinary patience. Over the first few 100 million years, the overdense seeds grew slowly, their density contrasts increasing from 1 part in 100,000 to 1 part in 1,000 to 1 part in 100. Eventually, the densest regions crossed a critical threshold and began to collapse inward under their own gravity. Dark matter halos formed first, invisible cocoons of gravitationally bound mass that provided the scaffolding for everything that followed. Within these halos, ordinary matter fell inward, heated by compression, cooled by radiation, and fragmented into the first clouds of gas dense enough to ignite nuclear fusion. The first stars were born. Over billions of years, stars lived and died and enriched their surroundings with heavier elements. Galaxies assembled from the merger of smaller protogalactic fragments. Galaxy groups coalesced along the developing filaments, flowing toward the nodes of the emerging cosmic web. The structures grew in mass and complexity over cosmic time, building the luminous architecture we observe today. In the regions that started with slightly less density, the opposite unfolded with equal patience and equal inevitability. A little less matter meant a little less gravitational pull. Neighbouring overdense regions stole what matter remained, drawing it outward along the gradients of the gravitational field like water flowing downhill toward a lower elevation. These underdense seeds expanded as their surroundings grew denser, becoming shallower and wider as matter drained out of them across hundreds of millions and then billions of years. They became the first voids, small at first, then larger as the drainage continued. And as dark energy gradually rose to dominance over the last several billion years, overwhelming the fading gravitational influence of the depleted matter within them, the expansion of these voids accelerated. The emptiest regions of the universe became emptier still, inflating outward against the thinning walls of the cosmic web with a momentum that will never be reversed. The entire architecture of the observable universe, every filament, every cluster, every supervoid stretching billions of light years across, traces its origin to quantum noise. Randomness at a scale smaller than an atom, operating during an interval shorter than any clock could measure, propagated upward through billions of years of gravitational evolution to produce structures so vast that light itself requires billions of years to cross them. The seeds of the KBC void were planted before matter existed, before atoms formed, before the four fundamental forces had fully separated from the unified state of the earliest cosmos. The largest void ever found began as a whisper of quantum probability in the first trillionth of a trillionth of a trillionth of a second. This connection between the infinitesimal and the colossal is one of the most remarkable facts in all of science. The cosmic web is not the product of some grand structural principle or organizing intelligence. It is the amplified residue of quantum randomness, a monument to chance built by gravity over cosmic time. The voids exist because certain patches of quantum foam happen to fluctuate downward rather than upward during an epoch so brief that no physical process could have controlled or directed the outcome. Had those fluctuations fallen differently, the voids would be in different places, the filaments would trace different paths, and the galaxies we know would never have formed. Every star in the night sky, every planet orbiting those stars, every atom in every living thing that has ever existed on any world owes its location in the cosmos to a random event that occurred before the universe was old enough to have properties we would recognize as physical. But the story of cosmic voids does not end with their origins. It continues into a future that extends far beyond the current epoch, and that future belongs almost entirely to the voids. Dark energy is accelerating the expansion of the universe. This acceleration has been measured through multiple independent methods, including observations of distant Type Ia supernovae, the geometry of the cosmic microwave background, and the clustering patterns of galaxies across cosmic time. It is one of the most firmly established and most deeply mysterious results in modern cosmology. No one knows what dark energy is. No one understands why it has the value it has or why it exists at all, but its effects are undeniable, and they are reshaping the cosmos on the largest scales. The acceleration is gentle at present, barely perceptible across the span of a single human lifetime or even across the lifetime of a civilization. Space is expanding faster with each passing second, but the rate of increase is slow enough that gravitationally bound structures, galaxies, galaxy groups, and some tightly bound clusters can still hold themselves together against the outward push. The gravitational attraction between the Milky Way and Andromeda is strong enough to overcome the expansion of the intervening space, and the two galaxies will merge in approximately 4 to 5 billion years regardless of what dark energy does in the meantime. The local group, our modest collection of roughly 80 galaxies, will likely remain gravitationally intact as a single coherent structure for the foreseeable cosmic future. Some of the most massive galaxy clusters, bound by deep gravitational wells filled with hot gas and dark matter, will persist as well. But outside these gravitational islands, beyond the boundaries where binding gravity yields to cosmic expansion, dark energy is winning. And it is winning fastest inside the voids. Where gravity is weakest, where matter is scarcest, dark energy faces no meaningful opposition. Voids are not just expanding, they are accelerating their expansion, growing faster with each passing epoch. The boundaries of voids push outward into the surrounding filaments, compressing them, thinning them, eroding the structures that define the cosmic web. Over timescales of tens of billions of years, this process will dismantle the web itself. The filaments will thin until they can no longer sustain the flow of matter between clusters. Galaxy groups that are not gravitationally bound will drift apart, their connections to the cosmic web severed by the expanding voids between them. Walls of galaxies will stretch and dissipate as the voids on either side grow larger and push them apart. Individual galaxies on the outskirts of groups will find themselves abandoned, their neighbours receding at ever-increasing velocities until they slip beyond the gravitational reach that once held the group together. The cosmic web, which today is the largest coherent structure in nature, a network of gravitational connections spanning the entire observable universe, will gradually unravel. Its threads will snap one by one. Its nodes will become isolated. The connective tissue that links distant parts of the cosmos into a single gravitational system will dissolve, replaced by ever-widening expanses of void that no signal, no particle, no force can bridge. The timescale for this dissolution is long but finite. Within roughly 100 billion years, an interval approximately 7 times the current age of the universe, the cosmic web will have largely disappeared. What remains will be a scattering of isolated galaxy clusters, each one a gravitationally bound island surrounded by an effectively infinite expanse of expanding void. These clusters will still contain galaxies. Stars will still burn within them, though the stellar populations will by then be dominated by dim, long-lived red dwarfs burning through their hydrogen fuel with agonizing slowness, each one capable of shining for trillions of years, but producing only a feeble fraction of the light our sun generates today. New star formation will have largely ceased as the available gas is consumed or expelled beyond recovery. The raw material for building new stars will simply run out. The clusters themselves will slowly evolve over trillions of years, their remaining galaxies merging one by one through gravitational friction until each cluster is reduced to a single enormous galaxy, a bloated elliptical containing the combined remnant mass of everything that once orbited within its gravitational reach. Beyond the edges of these island galaxies, the voids will stretch without interruption in every direction. The space between isolated clusters will expand so rapidly that light emitted from one cluster will never reach another. Photons that set out on the journey will find themselves running against an expansion that outpaces them, the distance growing faster than the light can cross it. Each island galaxy will occupy its own observable universe, a shrinking bubble of visibility within an endlessly expanding void. Over trillions of years, the cosmic microwave background will redshift beyond detection, its photons stretch to wavelengths longer than the observable universe itself. The evidence that a Big Bang ever occurred will fade from view. The other galaxy clusters, the ones that once shared the cosmic web and contributed to the grand architecture of the observable universe, will have vanished beyond the horizon one by one, their light redshifted into silence. From the perspective of any astronomer living on a planet orbiting a dim red dwarf within one of these island galaxies, the universe will appear to contain only their own galaxy. Every other structure will have receded beyond the cosmic horizon, carried away by the relentless expansion of the void into a darkness that is both total and permanent. Such an astronomer, examining the sky with whatever instruments their civilization has built, would find no evidence that the cosmic web ever existed. No filaments, no superclusters, no background radiation hinting at a hot, dense beginning. They would observe a single aging galaxy floating in an apparently infinite, static, and utterly empty void, and they would have no reason to suspect that the universe had ever been otherwise. This is the final state toward which the cosmos is evolving. Not a dramatic collapse into a singularity, not a violent tearing apart of atoms and particles in some catastrophic rip, not a cyclical rebirth that offers the hope of renewal. A slow, silent, inexorable expansion of emptiness. The voids will not merely persist as features of the cosmic landscape, they will consume everything they do not already contain. Given enough time, stretching into the trillions and quadrillions of years, voids will occupy not 80 or 90% of cosmic volume, but effectively all of it. The matter that once formed galaxies and stars and planets will still exist, locked inside cooling stellar remnants and slowly decaying black holes within isolated clusters, but it will constitute an infinitesimally thin fraction of a cosmos that has become, for all practical purposes, entirely void. The universe will not end with a bang. It will end with a silence so complete that there will be nothing left capable of noticing that it has fallen silent. There is a particular kind of disquiet that accompanies this picture. It is not fear, exactly. Fear requires an immediate threat, and the expansion of cosmic voids threatens nothing on any human timescale. The sun will exhaust its hydrogen fuel and swell into a red giant billions of years before the cosmic web unravels. Humanity, in whatever form it takes by then, will face countless challenges, more immediate and more personal than the dissolution of galactic filaments 100 billion years in the future. The disquiet comes from something else entirely. It comes from the recognition that the universe we see around us, the one filled with galaxies and glowing nebulae and the warm, steady light of hundreds of billions of stars, is not what the universe fundamentally is. It is a temporary arrangement, a passing configuration of matter that happens to exist during the brief cosmic epoch when the web is still intact and the voids have not yet finished their patient, relentless work of erasure. We live during the universe's most structured period. The cosmic web is at or near its maximum complexity right now, in this epoch, during this slender window of cosmic time. The filaments are as dense as they will ever be. The clusters are as rich as they will ever become. The voids are still bounded by walls of matter that have not yet been consumed. The contrast between the underdense regions and the matter-rich regions is as sharp as it has ever been and as sharp as it will ever get in the future. From this moment forward, measured across the timescale of billions and trillions of years, the trend reverses. The voids will grow, the web will thin, the contrast will soften and blur as matter spreads across ever larger volumes of expanding space. Structures that took billions of years to build will be erased by an expansion that never stops and never slows. What we observe tonight, when we point our telescopes at the sky and capture images of galaxy clusters and star-forming nebulae and the intricate lacework of the cosmic web, is the universe at its architectural peak. We are witnessing the cosmos at the moment of its greatest elaboration. It will never look like this again. Everything that follows, measured across cosmic time, is simplification, dilution, dissolution. The universe's future holds more darkness, more emptiness, more void. It is all downhill from here, measured in the currency of structure and complexity and light. The KBC void, the largest void ever confirmed, the structure that contains our galaxy and our supercluster and everything we have ever observed with the naked eye, is not an anomaly. It is a preview. It shows us what most of the universe already looks like and what all of the universe will eventually become. 2 billion light-years of underdensity, containing structure that is real but insufficient, hosting galaxies that exist but not enough of them, stretching in every direction around us so far that we cannot see the edges from inside it. This is not a peculiar corner of the cosmos. This is the cosmos. Most of it, right now, already looks like this. And the fraction that does not, the bright filaments and crowded clusters, is shrinking. What makes this terrifying, if that word still applies after hours of careful scientific exposition, is the completeness of the inversion it demands. Every instinct tells us that the universe is made of things. Stars, galaxies, planets, matter, energy, structure. We name the objects. We catalogue the structures. We map the concentrations. We build our understanding of the cosmos around the things we can see and measure. But the things we see occupy a sliver of the total volume. The overwhelming majority of the universe contains almost nothing, and that almost nothing is not a failure of the cosmos to fill itself. It is the cosmos expressing its fundamental character. The voids are not holes in the universe. The universe is the voids. The galaxies are holes in the emptiness, brief interruptions in a darkness that extends in every direction for distances the human mind cannot meaningfully comprehend. Every bright structure in the cosmos, every filament threaded with galaxies, every supercluster containing hundreds of thousands of worlds where beings might one day look up at the sky and wonder what lies beyond, exists as a narrow interruption in a void that stretches for billions of light years. The interruptions are beautiful. They are complex. They are, as far as we know, the only places in the universe where atoms have arranged themselves into configurations capable of asking what the universe is made of. But they are not what the universe is made of. They are the rare, temporary, luminous exceptions to a rule written in darkness and silence and absence. The largest void ever found is terrifying, not because of what lurks inside it. Nothing lurks inside it. That is precisely the point. It is terrifying because it is typical. Because the cosmos, when you step back far enough to see it whole, is not a cathedral of light. It is an architecture of absence, built from quantum noise and shaped by gravity and dark energy, into a structure dominated at every scale by the regions where matter chose not to gather. The galaxies we celebrate are the rounding errors, the voids are the sum, and the sum, stretching across 90% of all the space that exists, expanding faster with each passing billion years, consuming the filaments and walls and clusters that remain, is what the universe has been building toward since the first fraction of the first second. Not more structure, not greater complexity, not richer and more intricate arrangements of matter and energy, more nothing. That is the project. That has always been the project. And the universe is almost finished.